In 8.4, we learned a couple methods for proving triangles are similar. In 8.5, we're coming up with two new ones. The first one is side-side-side similarity theorem, and this is a little bit different with the sides. Like the side-side-side congruence theorem, if all three sides were congruent, then the triangles were congruent. But now with similarity, the sides need to be proportional. Okay, so the corresponding sides have to be proportional. And like side angle side, we need two sets of sides that are proportional and the included angle between. Very similar to side angle side where the angle has to be between. One quick example, that means if I have this triangle and this triangle, if I think these triangles are similar, the included angle, this angle, I'm going to make up some numbers, 2, 4, and we'll call this 1 and 2. These sides are proportional. The angle between these are congruent. So you'd set this up 2 over 1, and then you'd say that equals 4 over 2. This side and this side. So set up your proportional parts and the angle between. We don't need an angle over here. The angle has to be between the two proportional sides. Which of the following three triangles are similar? Notice I have nothing about angles, so I have to solve this by side-side-side similarity. I'm going to write this all out. The shortest side, the ratio of the shortest sides would be, use 3 to 6 for this triangle. The ratio of the longest sides, 7 to 18. So I start looking at these ratios, 3 to 6, 7 to 18. Are those the same? So right away, I know it would have to be 9 over 18 to be the same as 3 to 6. So these are not. As soon as I find one set of corresponding sides that aren't congruent, then they are not. Now I can check a different set. So let's try these ones. Okay, let's try the shortest sides first. So 6 to 10. The longest sides would be 18 to 30. Well, 3 times 10 is 30, 3 times 6 is 18. So far they match up, but we got to check all three sides. And the last set with the remaining sides, 15 to 25. Does that work? So looking at this, 3 to 10 is the same thing as 3/5. Now looking at that as 3/5, I know 3 times 5 is 15, 5 times 5 is 25. All three sides of these are proportional, so these triangles are. If these are similar and these are not, you could rule this one out. These are not going to be, because these are the same shape, not the same size. But these ones are different shapes. Well, these ones aren't going to be the same, right? That's kind of a common sense thing. So we found those ones are similar. In this next example, describe how we can show that triangle ACB is similar to BCE. And we know AC, I like to label my diagram, is 6. AD is 10. And looking at this, I don't think my numbers look very well, but if AC is 6, this length, well, if AD from here to here is 10, well, 6 plus this is going to be 4. We're going to go with it even though it doesn't look right. If BC is 9 and BE is 15, so from here to here is 15, this would have to be 6. and that's the information they give us. So we know nothing about this side. So this, we know nothing about this side and the corresponding side. So that rules out side, side, side similarity. So we need to use, so I'm going to use side, angle, side. Okay, makes sense. So what angle do I know is congruent? Well, it just so happens this angle between these two sides, the included angle, they're going to be congruent by vertical angles. And so if those are congruent by vertical angles, these triangles are similar by the side angle side similarity theorem. Right? Let me double check. Those theorems? Yeah, thought they were. Okay, and it doesn't make a huge difference, theorem or postulate. One thing you can do with similar triangles is something called indirect measurement. You can measure something without actually putting the tape measure across it. One thing, for example, would be to, if I wanted to measure the length across the pond in Lanesboro, I'm going to scroll down a little bit. This is where you are in my math class. This is the high school. Here's the gym. Here's the back parking lot and down the hill. This is the Lanesboro Pond. If I want to know the distance across, it'd be pretty hard to actually put a tape measure across this. But what you can do is you can set up a right triangle on this side of the pond. Okay, make this a right angle, and you can measure these distances. I know a 3, 4, 5 right triangle, so you can set it up like that. And then if you come over to this side, and I shouldn't use green, let me use purple here, maybe that show up better. I can come over here and if you put like a cone here or something that you could see, keep this a nice straight line. Okay, and make this a right angle. Okay. Now, if you knew this distance, I'm just going to make up a number, let's call it 50. If you knew this distance was 50, you could, these triangles are similar because angle, angle, and these are vertical angles, so they're similar by angle, angle. And then you could set up a proportion to figure out this length. Okay, this side is going to correspond with this side, so you could say x over 3 equals, and the 50 corresponds with the 4, and then you could cross multiply and divide. You get 150 divided by 4, which is almost 6, or excuse me, it goes in there almost 4 times, so it'd be 3, 12, you'd be left with 30, 4 goes into 37, so it'd be approximately, I should change that, 37 feet across if we set it up like this and it worked. Okay, so that's an indirect measurement. We measured this length by using similar triangles. One of the world's tallest flagpoles is in, do I have it written down? Forget what country this is, but it's a really big flagpole. And the flagpole pictured casts a 22.5 meter shadow. A 2 meter tall person stands near the post and casts a 35 centimeter shadow. So notice we probably want to change this to 0.35 meters. So we have the same units. And you could set up a proportion and indirectly measure this. You're not actually climbing up this pole to measure it, right? The pole's shadow, 22.05, compared to the person's shadow, the corresponding part in those triangles, right? If you imagine you have a triangle being formed here, and this angle of the sun coming down is going to be the same for the little tiny person over here. It's going to be the same angle. So these triangles are similar. So shadow to the shadow, the pole's height to the person's height. Now you can cross multiply and divide. And I'll leave that calculation up to you to figure out how tall that flagpole actually is. There's your homework. If you got questions, let me know. Talk to you later.